Hello, and welcome back to the channel. Little More Learning is back with Season 2 of System Design. In Episode 1, we're exploring load balancers, the unsung heroes of the Internet. At its core, a load balancer acts as a sophisticated traffic controller within a network. Its primary function is to intelligently distribute incoming client requests across multiple backend servers or server farms. This prevents any single server from becoming overwhelmed, which would lead to performance degradation or outright failure. You can think of it as a highly efficient bouncer at a busy event, directing attendees to available entrances and ensuring no single point becomes congested. This strategic distribution is what guarantees high availability and consistent, reliable performance, enabling systems to gracefully handle millions of concurrent users. The importance of load balancing becomes clear when we consider its absence. Without it, all incoming traffic would funnel to a single server or a limited set of resources, inevitably leading to system crashes or severe slowdowns under any significant load. With a load balancer in place, traffic is intelligently spread, ensuring individual server workloads remain manageable and overall system performance stays smooth. This capability is pivotal because it facilitates scaling out, the process of adding more server instances horizontally to distribute load, rather than just scaling up, which involves simply enhancing the resources of a single server. It's absolutely critical for managing peak demands in scenarios like massive e-commerce sales during holiday seasons, large-scale live streaming events, or the synchronous login surges during online examinations. Load balancers have evolved over time, and we categorize them into a few key types based on their implementation. Hardware load balancers. These are physical appliances, dedicated pieces of network hardware. While they can offer high performance, they are typically expensive, require significant upfront investment, and lack the agility needed in dynamic cloud environments. Software load balancers. These are applications, such as NGINX or HAProxy, that run on standard servers or virtual machines. They offer much greater flexibility, are generally more cost-effective, and can be deployed rapidly. Cloud load balancers. These represent the current industry standard. Provided as managed services by cloud providers like AWS, with Elastic Load Balancing, ELB, or Azure, with Azure Load Balancer. They are highly elastic, auto-scaling, and deeply integrated into the cloud ecosystem. They automatically adjust capacity to handle fluctuating loads without manual intervention. Once a request arrives at the load balancer, an algorithm determines which backend server should process it. Key algorithms include round robin. This is the simplest strategy, distributing requests sequentially across servers in a cyclic manner. Least connections. A more intelligent approach. It directs the incoming request to the server that currently has the fewest active connections, ideal for long-lived connections. IP hash. This algorithm hashes the client's IP address to consistently direct subsequent requests from the same client to the same server, ensuring session stickiness. This is useful for applications that store user session data on specific servers. Random. Occasionally, a simple random selection from the server pool is used, especially in very large, homogeneous environments. Weighted round robin, an enhancement where servers are assigned weights based on their capacity, ensuring more powerful servers receive a proportionally larger share of requests. For instance, Netflix employs a sophisticated mix of these strategies to efficiently manage traffic across its vast global network. Load balancing can operate at different layers of the OSI model, primarily Layer 4, Transport Layer, and Layer 7, Application Layer. This distinction dictates the level of intelligence available for routing decisions. Layer 4, Transport Layer, Load balancing. This operates based on network information like IP addresses and port numbers, TCP/UDP. It's generally faster and has lower overhead because it doesn't inspect the content of the application data. It simply forwards packets to an available server. Layer 7, Application Layer. Load balancing. Operating at the application layer, this type can inspect the actual content of HTTP/HTTPS requests, including headers, cookies, and URL paths. This allows for much smarter routing decisions, such as directing requests for /videos to a video-specific server farm while sending /auth requests to an authentication service. While offering greater flexibility and intelligence, Layer 7 load balancing introduces slightly more latency due to the deeper inspection required. The choice between them depends on whether your routing needs are simple and fast, L4, or complex and content-aware, L7. To visualize a load balancer's position, consider its strategic placement. Primarily, a load balancer resides between the clients, your users' devices, and your backend servers, which host your application logic and data. However, in modern, complex distributed systems, load balancers aren't confined to the edge. They can also exist within the system, for instance, managing traffic between different microservices in what's known as a service mesh. Large-scale architectures frequently employ multiple layers of load balancers. Edge LBs. These are the first point of contact for external internet traffic, often integrated with CDNs like Cloudflare or provided by cloud platforms like AWS ELB to distribute global traffic. Internal LBs. Once traffic enters your private network, these distribute it further to different tiers of your application or specific microservices. This multi-layered approach enhances resilience, optimizes performance, and provides granular control over traffic flow. Let's consider a highly relatable real-world example, an online examination portal. Imagine the precise moment an exam begins, a sudden, massive surge of login requests from thousands of students. Without a load balancer, this immense, synchronous traffic would almost instantly overwhelm a single application server, leading to a crash or unresponsiveness, disrupting the exam for many students. With a load balancer, the load balancer intelligently distributes these login requests across a pool of multiple backend servers. Crucially, it can also integrate with auto-scaling groups in the cloud, dynamically provisioning and deprovisioning additional servers in response to traffic surges. Furthermore, health checks continuously monitor server status, automatically removing any unresponsive servers from the pool and reintroducing them when they recover. The outcome is a system that remains stable and responsive throughout peak load, ensuring a smooth experience for all participants. This demonstrates how load balancers are indispensable for uptime in high-stakes, high-traffic scenarios. Modern load balancers offer a suite of powerful features that extend far beyond simple traffic routing. Health checks continuously monitor the operational status of backend servers. If a server fails a check, it's temporarily removed from the pool to prevent requests from being sent to a broken instance. SSL termination. This feature offloads the computationally intensive process of encrypting and decrypting SSL/TLS traffic from your backend application servers to the load balancer. This frees up your servers to focus on core application logic, improving their performance. Sticky sessions. Session affinity ensures that all requests from a particular user's session are consistently routed to the same backend server. While useful for stateful applications, it can complicate horizontal scaling by unevenly distributing load. Rate limiting. protects your backend infrastructure by limiting the number of requests a single client or IP address can make within a specified time frame, effectively mitigating abuse and certain types of denial-of-service attacks. Global load balancing, GLB for applications deployed across multiple geographic regions. GLB directs traffic to the nearest or most performant data center based on factors like latency or server health, optimizing user experience and enhancing regional resilience. As you delve deeper into system design, familiarize yourself with these essential load balancing tools. NGINX, a highly flexible and widely used open-source software load balancer, capable of operating effectively at both Layer 4 and Layer 7. It's known for its high performance and customizable configuration. HAProxy, another popular open-source choice. HAProxy is renowned for its high performance, particularly in handling TCP and HTTP load balancing for demanding, high-concurrency environments. AWS ELB, Elastic Load Balancing Amazon Web Services Managed Load Balancing Service. It offers automatic scaling, deep integration with other AWS services and various types, including application load balancers, Layer 7, and network load balancers, Layer 4. Cloudflare, while primarily a CDN and security provider, Cloudflare acts as a powerful edge load balancer, directing traffic globally, providing DDoS protection, and enhancing performance right at the internet's edge. The optimal tool choice depends on your specific scale, budget, and the level of control and features you require. While powerful, load balancers aren't without their potential pitfalls, and awareness of these gotchas is crucial for robust system design. Too many layers equals latency. Introducing excessive layers of load balancers can cumulatively add network latency to every request, impacting user experience. Misconfigured health checks equals false positives. If health checks are poorly configured, they might prematurely remove healthy servers from the pool or, conversely, keep truly failing servers active, both leading to service disruptions. Sticky sessions equals harder to scale statelessly. Over-reliance on sticky sessions makes it difficult to achieve true horizontal scalability and maintain stateless backend services, as specific user sessions become tied to particular servers. ELB itself can become a single point of failure. Ironically, if the load balancer itself isn't redundant, it can become the very single point of failure it was designed to prevent. The solution involves deploying load balancers in highly available configurations, such as active-passive pairs or active-active clusters. Understanding these challenges allows for more resilient and efficient system architecture. In conclusion, load balancers are an absolutely fundamental and non-negotiable component in any scalable and resilient distributed system today. They are the guardians that keep systems alive and responsive under any traffic condition, from the high-volume social media platforms to critical online examination systems. To truly master these concepts, remember these key takeaways. Understand your layers. Differentiate clearly between Layer 4 and Layer 7 load balancing, as this choice impacts performance and routing intelligence. Know your algorithms. Familiarize yourself with common algorithms like round-robin, least connections, and IP hash, and understand their appropriate use cases. Choose the right tools. Be aware of the major load balancing tools and services, and select the best fit based on your specific scale, budget, and application logic. Mastering these principles is a vital step toward building the high-performance, fault-tolerant digital systems that power our modern world. Before you go, I'd love to hear from you in the comments. If you found this video helpful, do give it a like, share it with your friends, and of course don't forget to subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.